Greetings all. Here's our old friend adenosine triphosphate, or ATP. I bet you already know that in biochemistry we're going to couple the hydrolysis of ATP, which is a strongly exergonic reaction, in order to pay for most or almost all of the endergonic reactions we have to do in biology. Looking at the structure, these hydrogens here are acidic and at a physiological pH of around 7.4. 3 or 4 of these have ionized, depending upon the pKa values for each hydroxyl group. I couldn't find a good reference for exactly what these pKa values are for ATP, but it probably varies from cell to cell and from moment to moment, depending upon things like the magnesium ion concentration. So here's a potentially good idea. Let's ignore all of that, because it's easier to keep track of all of the hydrogens if we show them as hydroxyl groups in these chemical structures, and not worry about which ones happen to be ionized right now. We'll build a molecule of ATP one piece at a time, starting with ribose. Ribose is a 5-carbon monosaccharide. In aqueous solution, it exists in some combination of a straight chain structure and at least 4 different ring structures. This structure here is beta-D-ribofuranose, but I'm not showing the stereochemistry because we're trying to avoid as many of the horrible details as possible. This molecule over here is adenine, which is one of the 4 nucleobases found in DNA, or one of the several nucleobases found in RNA. We have some horrible details for adenine as well, like whether the hydrogen is on this nitrogen, or whether this hydrogen is on this nitrogen. These 2 structures are called tautomers, which is when a compound has 2 or more structural isomers that can easily switch back and forth. This is the one we're going to use to make ATP. To connect the adenine to the ribose, we're going to use our favorite trick in biochemistry for making molecules bigger, the condensation reaction. We're going to pull out 2 hydrogen atoms and 1 oxygen atom to make a brand new water molecule to make an N-glycosidic bond between the adenine and the ribose. When that happens, we get a new name. Ribose plus adenine is adenosine, a nucleoside. Now we're going to bring in a molecule of phosphoric acid and do our same trick with a condensation reaction to make a phosphoester bond. Adenosine plus a phosphate is adenosine monophosphate. Adenosine monophosphate, or AMP, is a nucleotide. We can bring in a second molecule of phosphoric acid, make another condensation reaction. This time we're making a phosphoanhydride bond. And here comes a third molecule of phosphoric acid, making a second phosphoanhydride bond and giving us our old friend, ATP. The phosphoanhydride bonds are the high-energy bonds in ATP. For the hydrolysis of ATP, ATP plus a water molecule gives us adenosine diphosphate, plus Pi, which is just a shorthand way to write a phosphate ion, plus energy. Or we can clip off 2 phosphate groups at one time, so ATP plus water equals adenosine monophosphate plus pyrophosphate, PPi, plus energy. The pyrophosphate quickly and spontaneously hydrolyzes into 2 phosphate ions in aqueous solution. This energy is about the same as this energy until the pyrophosphate hydrolyzes. After the pyrophosphate hydrolyzes, this energy is about twice the energy of the ATP to ADP reaction. So you still get your money's worth out of these 2 phosphoanhydride bonds. Why the phosphoanhydride bond is the high-energy bond in ATP might not be all that obvious. If we look at something familiar, like the combustion of methane, methane plus oxygen gives us carbon dioxide plus water plus energy. The carbon atom in the methane is getting fully oxidized to make carbon dioxide, and the hydrogen atoms are getting fully oxidized to make water molecules. And from general chemistry, when we're oxidizing chemical bonds, we're releasing energy. That at least seems familiar. But the phosphate ions that we're clipping off of ATP, they're already highly oxidized, so that can't be why these reactions are exergonic. We're going to try to ignore as many of the horrible details as possible, but the hydrolysis of ATP is exergonic because 2 main reasons. The negative charges on the phosphate ion are now getting farther away from the remaining negative charges on the adenosine diphosphate as the phosphate ion floats away. And our second reason is resonance stabilization. The who with the what now? Let's pretend we can paint a number on each of these 4 oxygen atoms in this HPO4-2 phosphate ion so that we can tell the oxygen atoms apart. The double bond can be on oxygen number 1, with a hydrogen on oxygen number 2, and negative charges on oxygens number 3 and 4. Or the double bond on oxygen number 1, the hydrogen on oxygen number 3, negative charges on oxygens number 2 and 4. Or the double bond on oxygen number 4, the hydrogen on oxygen number 3, the negative charges on oxygens number 1 and 2, and so on. When I was sketching these out on a piece of paper, I counted at least 16 different resonance structures for this phosphate ion, and I might have missed some. More resonance structures equals more entropy, and the universe likes entropy. So our 2 reasons why the phosphoanhydride bond is a high-energy bond: we're moving negative charges further apart from each other, reducing electrostatic repulsion, and we're making a whole bunch of entropy through our old friend resonance stabilization. So the hydrolysis of ATP to make ADP in a phosphate ion, delta G0 is around negative 30 kilojoules per mole. One of the horrible details in biochemistry, though, is that conditions inside a cell are not at all close to standard conditions. So the delta G0 under the standard chemistry kind of standard conditions of 298.15 K, 1 mole per liter of reactant and product, pH 7, etc., those aren't very relevant to biology. So I'm going to use this symbol, delta G0 prime, or delta G degree prime, or delta G naught prime, however you want to say that inside your head. Delta G0 prime represents the, yes, but in human biochemistry, standard conditions are around 310 Kelvin, concentrations of ATP, ADP, and phosphate are in the millimolar to micromolar range, pH of 7.4, and so on, those kind of standard conditions. Delta G0 prime tells us where the equilibrium constant, KEQ prime, is under these more biologically plausible standard conditions. By the way, if the hydrolysis of ATP is ever at equilibrium, that would be an excellent definition of dead. In a living cell, we keep the ratio of ATP to ADP on the order of several to 1 to several hundred to 1 ATP molecules for every ADP molecule. For the hydrolysis of ATP, the delta G0 prime is around negative 40 kilojoules per mole, quite a bit more exergonic, under biologically plausible standard conditions. Now we can use our old friend this equation, delta G equals delta G0 prime plus RT natural log of Q, where Q is the reaction quotient, the ratio of the relative concentration of ADP times the relative concentration of phosphate ions divided by the relative concentration of adenosine triphosphate. And we're using these relative concentrations to make Q a dimensionless number, and it also lets us ignore the water molecule. Assuming we can make reasonable estimates of what these concentrations are inside the cell or organelle or whatever compartment we're looking at right now, then we can calculate what the delta G should be. And here's a big table doing that. By the way, we definitely need to include the phosphate ion concentration when estimating Q. We can't just use the ratio of ATP to ADP. Phosphate ions have many jobs inside a cell, besides just ATP, so the phosphate ion concentration in a cell is high enough to matter. Summary. We did some terminology: nucleobase, nucleoside, nucleotide. The phosphoanhydride bonds are the high-energy bonds in ATP. And under biologically plausible conditions, the delta G for the hydrolysis of ATP can be from around negative 50 kilojoules per mole to maybe something more like negative 75 kilojoules per mole. Okay, I apologize that this video was so much longer than the others. Thanks very much. I'll talk to you later.